We'll start with a demotivational poster, not because I want you to be unmotivated, but because it's funny. Many times in design, things don't go as you had hoped or planned, and the first prototype doesn't work, the rocket ship crashes on the launch pad, you have to get up and try again. So this is less to demotivate you and much more to just laugh when problems happen. So let's start off with this one, potential. Not everyone gets to be an astronaut when they grow up. Now, obviously, if you're riding on top of the first rocket, that's probably a good thing. You really don't want to be the first astronaut on the first rocket. You're very likely to die. As a matter of fact, the first few rockets didn't have people on them as far as our space program goes, for good reason. So this is MET 314. It's machine elements, and this is our class introduction. So let's have a working definition for the class. Machine elements is the study of the components and devices that are coordinated and integrated into a system that meets a customer's needs. So that's our working definition. So remember, we're not trying to focus so much on the machine elements, although that's what we will study in detail. We're trying to learn how to master these design procedures so that we can use these machine elements to solve whatever problem the customer has. Sometimes the appropriate solution is a drive that involves a gear set. Other times the appropriate system is a drive that involves a pulley and belt system. It just depends on the application and what the customer requires. So this is the class you probably thought you were signing up for all of your 4 years studying mechanical engineering technology. However, you probably quickly realized that there's a lot you didn't know about statics and dynamics and materials, and you've studied a lot on all of those topics, and that has laid a nice foundation for you so that you can understand this class. So we're going to cover belts and chain drives, gears, keys, couplings, seals, all the things that you see in this list, and probably even some more before it's all said and done. So these are the topics we'll cover, and we'll cover them one after the other, not in this order, but in an order that I think is appropriate so that you can accomplish the project that I have for you in the class. We're not going to cover all of the chapters in our text. Chapters 1 through 6 really are review or information that is not completely necessary. The most important part of chapters 1 through 6 is a review of strength of materials. Since you've already had a separate course on the topic and of course a separate text on it as well, we won't go through these. There will be some things that we will refer to in this portion of the text, but I'll point out page numbers and particular topics that you need as we go along. So that's the beginning portions of the book, and we cover the remaining chapters. There may be 1 or 2 chapters we don't cover, I don't recall, but 7 on are the chapters that we will cover. So what is mechanical design? Well, there are many aspects to it. One is the function of what the device has to do, and just general statements about the device. So it has to support a load, for example, lift a crate, maybe transmit power. Design requirements are more specific, they're more detailed, they're quantitative, there's numbers with them. Okay, so I forgot, hold 2 structural members together is a functional requirement, but design requirements are more like accelerate from 0 to 60 in 5 seconds. Has to operate between -20 and 140 degrees, must be made of polyethylene to resist acid or some other material. And then the evaluation criteria are things that are desirable to have, ways that we're going to evaluate the design and decide whether or not it's a good design. So for example, must be inexpensive or must be aesthetically pleasing, must appear rugged. These are evaluation criteria that are important. The last one got me one time. It was really interesting. I was working for Amatrol, and I needed to design a device for holding bolts. We were going to have a robot automatically assemble bolts into a valve body assembly. And there are many different ways to hold bolts. One way is to palletize them. What that means is that the bolts are laid out in a known pattern so the robot can just remember which bolt it's at, go to a particular position, pick it up, and use it in the assembly. Well, if you just lay them out flat, they take up a lot of space. Hanging a bolt is better because, of course, then the projected area is just the diameter or the cross-sectional area of the bolt and the head and so forth. I made a device that had a spiral shape and sort of a daisy shape as well, and the daisy shape turned. It was all out of sheet metal, so it was inexpensive to make, And the spiral, basically the daisy fingers move the bolt around through the spiral so that the bolt advanced in the spiral, so that there was only one what's called pick position. So the position where the bolt would be presented was just one position, and you could program the robot to just know to go to one position over and over. It made the robot part a lot easier. Now, I also had a stop in it so that I could have a motor just continuously run with this thing, and the motor would have an overrunning clutch, so not an overrunning clutch, but a friction clutch, so that if a bolt came into position and couldn't get out, the motor would just keep turning, but it would slip. It was a great little design, and when I showed it to my colleagues, they looked at it and said, "Yeah, that's nice, that's a good idea. It certainly does give us a compact storage for the bolts, but it doesn't look rugged. It looks like a joke. It looks like a toy. We can't use this." And that made sense. I hadn't really thought of it from that angle to that point, and I wasn't upset because my colleagues said, "Let's not use this." I simply agreed with them because our products at Amatrol were for training, and if the students didn't respect the equipment and didn't feel like the equipment was real industrial equipment or something like it, they wouldn't respect the training. And so there's a very good reason that we couldn't use this. So that was a desirable qualitative characteristic that we had to have. Here's the design process, and most texts will lay out the design process something like this, where you've got defining specification, create concepts, decide which one, and then create the detailed design. I will tell you the design process is never so linear, and when you get to senior capstone and you're designing a solution to some problem, you will find that you iterate over and over. You might get to the point where you're ready to do a detailed design, or you might start the detailed design and you realize, wait a second, if we just XYZ, it would be so much better, and you have to go back, so thus the term going back to the drawing board, and say, well, wait a second, maybe I could change the specifications and what's required. Now, a lot of times people would say, well, that's not appropriate, the specifications should come from somewhere else. But honestly, the design process needs to be flexible in order to produce high quality. And if you study quality control, you'll find that everything is viewed as an iterative process, something where you're continuously improving in order to reach some great design. There's no designs I know of that the first prototype it works great and we're done. No, every design is changed. You get done with it, you produce it, and you realize, oh, it would be a lot better if I would do this instead. You never want to buy the first car off the assembly line, right? It's going to have problems. You want to wait until that model year has been out a couple of years and then buy a car that's had the bugs worked out of it. So while your author presents the design process as a linear process, it really is not, although we try to do it in some semblance of order. There's a nice example on page 10. I'd like you to glance through that and try to understand. It'll make some sense with this design procedure. When you're designing, there are preferred sizes. Let's say that I ask you to calculate the required diameter for a bolt, and you come up with 0.24059 inches, or better yet, let's say 0.2405 inches. Well, I would expect you to use a 1/4 inch bolt, which is 0.25 inches in diameter. So there are preferred sizes. Why? Well, imagine trying to ask for a fastener that is 0.2408 or 9 or whatever it was inches in diameter. Well, that's not a standard size, and you're going to pay quite a lot to get a custom fastener like that. Not only that, but when you're designing even a plate or locations of holes in a plate or anything like that, you'd rather use preferred sizes, unless there's a very good reason for not using them. And one very good reason, if you make a shop print that has English units but you're using a metric bearing or something, you might call out the hole for the bearing in English units, but of course it's going to be some odd number. It won't be a preferred size, but the reason is because the bearing has to fit well. So that is something that's an example where there's a exception to the rule. But you really should prefer to use preferred sizes. And there's first, second, and I believe third preferred sizes. I'm looking on the page. It's page, I don't have the page numbers here. I've got the appendices. It's page 722 and 723. And you should tab these pages in your book. Yeah, they've only got first and second preferred sizes. Now there are standard sizes for screw thread as well. And I'll tell you just a quick hint. 632 threads are a standard size, but most machinists hate this size. The reason is because the 32 threads per inch and the number 6 diameter ends up generating a relatively large tooth for a relatively small fastener diameter. What ends up happening when you try to make this thread in material, if you're tapping it, a lot of times the teeth break off in the tap, not the teeth, excuse me, the body of the tap breaks because the body is so small by comparison to relatively large cutting tooth. And so 632s are, although they are a preferred size, please try to avoid them. The machinist will thank you for it and you'll get more out of them. They'll be friendlier with you and so forth. So just a nice little hint and something to know. Let's see. There are structural steel shapes you need to be aware of. It's one of the things in the first 6 chapters. In fact, it's in the first chapter. I'll show you a page number here in a second and what you're looking for. Some more information. In English sizes, 0 through 12 are the numbered basic size diameter, but from a quarter up are the fractional fastener sizes. And this is for preferred sizes as well. Well, in preferred sizes, actually, yeah, preferred sizes don't go with numbers. The 0 through 12 are just for fasteners. I couldn't recall if any preferred sizes were listed as screw thread diameters. I didn't think so, but wanted to double check. And in the case of a fastener, 32 means 32 threads per inch. So a 632 has 32 threads per inch. And then the number 6 is the major diameter, or nominal diameter, really. It's not a number 6 like a measurement on a tape. It doesn't really correspond to the number of inches or fractions of an inch. But it's just the numbered sizes. And a number 12 size actually is not very common. A number 12 size is actually very close in diameter to a quarter-inch fastener, so they're not used commonly. In the metric designation, M means metric, 10 millimeters the basic diameter, and then 1.5 means there's 1.5 millimeters between the threads or between the turn. That's the amount of advancement in the turn of the screw. It's also called the pitch. So here's the structural steel shapes I wanted you to know about. Some information's about them to show what they're called on page 17. You may want to go back and look at that. But there is a table in the back of your book for detailed information about all these structural steel shapes so that you can design out of them. There's something else I wanted to say here. Oh, we also had tables like these in your text for 211, so they may look a little bit familiar to you. There are several pieces of software you'll want to use in this class. The most important one is Excel. I highly recommend Excel for your calculations because often when you're designing, you'll get to the end of the design, you'll realize that you have to change things, but in your work, I expect you to write out the equations and show me what you're using as well. You can't just, I mean, you could just turn in an Excel sheet and reference which equation numbers you're using. That's okay. And I've had several students go through the class and do that, and it kept them organized. It also helped them remember where all the equations are located. The tests are all open book, open notes, so you can put a tab in your book. In fact, I highly recommend tabs throughout the book, and I'll tell you where to put them. We've already found one page 722 and 723 for sure, that you need a tab on to find out what preferred sizes are. But there's another useful piece of software. It's called mDesign. And I've got a file where you can download it and install it on your computer. But it's a piece of software that has most of the formulas and material information that's in the text in the program and can do design for you. Now, I do not accept just mDesign solutions for things. I want you to crank through the numbers yourself. But mDesign is a nice way to verify the work that you've done to see if you've performed your calculations correctly. MD Solids is on this list. I don't really recommend it all that much. It's okay. Honestly, everything that MD Solids can do, really, a combination of mDesign and SolidWorks can accomplish. And I should really have SolidWorks on this list. I forgot it. But you definitely need to use SolidWorks in this class. So make sure you brush up on it, and if you don't have a license, maybe you should get one, a student license or something. Of course, we have SolidWorks available in the lab for you.